Algebra 2, Chapter 5, Section 6, Complex Numbers. In this lesson, we're going to learn to identify and graph complex numbers, add and subtract and multiply complex numbers as well. Okay, when we learned to count, we used what we call the natural numbers, 1, 2, 3, 4, and so on. Your number system has grown to include other types. You have used real numbers, which include both rational, such as 1/2, and irrational, such as square root of 2. Now on your number system, your number system will expand to include the numbers such as negative or square root of -2. The imaginary number I is defined as a number whose square is -1. So I squared equals -1. And in essence, I equals the square root of -1. An imaginary number is any number in the form of a plus bi, where b is not equal to 0. So here's what we need to know. For any positive real number a, the square root of -a is I square root of a. So example, square root of -4 we can rewrite as I square root of 4, which could be I times 2, which we can convert to 2i. Note that the square root of -4 squared is not the same as 4. Square root of -4 is going to be I times square root of 4 squared. So it's going to be I squared times the square root of 4 squared, which would be -1 times 4. So it would be -4. So simplify using I. So here's the first example. We'll just kind of walk through this one together. Simplify the square root of -8. Well, the square root of -8 is the same as the square root of -1 times 8, which is the same as square root of -1 times the square root of 8. Well, square root of number 1, the square root of -1 is I. So it's I times square root of 8. We can simplify the square root of 8, which is I times 2 times square root of 2. We could rewrite 2i square root of 2. Okay? So, moving on, let's check these out. 1a. So if you see a negative, you could automatically just pull the I out and say I square root of 2. But if you don't see that, you could rewrite the square root of -2 as the square root of -1 times the square root of 2. Square root of -1 is I square root of 2. Answer C. Okay, 1b. Again, you could look at it as this, so it's equal to square root of -1 times the square root of 12, which would be I times the square root of 4 times the square root of 3. So we could say this is 2i square root of 3. Answer is D. The other way you could really look at it is you see the negative sign, just pull the I out. So it's I square root of 2. It's I square root of 12 right now. And then it's going to be I square root of 12 breaks down to square root of 4 times square root of 3. So again, we're getting to the same spot we did before. We're just saving a step. So simplify square root of -36. So that's going to be I 6i. How did I get that so fast? Well, square root of -36 is the same thing as square root of -1 times square root of 36. Square root of -1 is I, and the square root of 36 is 6. So the answer would be 6i. Okay? Imaginary numbers and real numbers together make up a set of complex numbers. A complex number can be written in the form of a plus bi, where a and b are both real numbers. So you have a real part, which is a, and an imaginary part, which is bi. Simplify imaginary numbers. Okay? Write the complex number square root of -9 plus 6 in the form of a plus bi. Well, step 1, I'm just going to flip it. So I got 6 plus the square root of -9. 6 plus, remember that negative sign just means I square root of 3. Sorry, square root of 9. What's the square root of 9? 3. So it's just going to be 6 plus 3i. Okay? Write a complex number in form of a plus bi. Well, I could rewrite this as 7 plus the square root of -18. So I could say 7 plus I square root of 18. Square root of 18 is the same thing as square root of 9 times the square root of 2. So I can say 7 plus square root of 9 is 3, 3i times the square root of 2. Okay? Moving on. The diagram below shows a set of numbers that are part of the complex number systems. Okay, we've done this before. We start with the natural numbers, the whole numbers, the integers, the rational numbers, the irrational numbers, which are all real numbers, and then now imaginary numbers, anything with an I in it. So you can use the complex number plane to represent a complex number geometrically. Locate the real number on the horizontal axis and the imaginary part on the vertical axis. So you can graph 3, negative 4i in the same way you'd graph 3, negative 4 in the coordinate plane. The absolute value, okay, understand this. The absolute value of a complex number is the distance from the origin on the complex number plane. You can find the absolute value by using the Pythagorean theorem. So in general, a plus bi, the absolute value of a plus bi is the same thing as the square root of a squared plus b squared. Okay? So, find absolute value of 5i. Since 5i is 5 units away from the origin, so on the imaginary axis, 5i is going to be 5. Find the absolute value of 3 minus 4i. So it's going to be the same thing as the square root of 3 squared plus negative 4 squared. All right, so once you do the math, that's going to become 5. So let's look. Find 6 minus 4i, the absolute value. So that's going to be the same thing as the square root of 6 squared plus negative 4 squared. So that's going to be the square root of 36 plus 16, which that's going to be the square root of 52. See 52, I can pull out a 4 and a 13. So the square root of 4 times the square root of 13. So that's going to be square root of 4 reduces to 2 times the square root of 13. So the answer is 2 square root of 13. Next example, negative 2 plus the square root of, or negative 2 plus 5i. Find the absolute value of that. So that's going to be the square root of negative 2 squared plus negative 5 squared. So negative 2 squared is 4. Negative 5 squared is 25. So the square root of that, which would be the square root of 29. And I don't think you can reduce square root of 29 anymore, so the answer is B, square root of 29. All right, find the absolute value of 4i. It's just going to be 4. Okay, any questions on that? All right, objective 2, operations with complex numbers. You can apply the operations of real numbers to complex numbers. If the sum of two complex numbers is 0, then each number is the opposite or the additive inverse. So let's go look. Example of the additive inverse of a complex number. The additive inverse of negative 2 plus 5i, just flip the signs, it'd be 2 minus 5i. That's the easiest way to do it, just flip the signs. Find the additive inverse of negative 5i, just be positive 5i. Just flip the sign. Find the additive inverse of 4 minus 3i, it'd be negative 4 plus 3i, just flip the signs. Answer C. Find the additive inverse of a plus bi. Be negative a minus bi. Just flip the signs. Okay? Moving on. To add or subtract complex numbers, combine the real parts and the imaginary parts separately. So simplify the expression 5 plus 7i plus negative 2 plus 6i. So we just sum like terms. So it's going to be 5 and negative 2, which would be 3. 7i and 6i, can add those together, just be 13i. Okay? So simplify. Remember, you got to distribute that negative sign. So it's going to be 8 plus 3i minus 2 minus 4i. Don't forget to distribute the negative sign. So now it's just sum like terms. So let's sum like terms. 8 and negative 2 is positive 6. 3i and negative 4i is negative I. So it'd be 6 minus I. Answer is B. Okay, again, distribute the negative sign. So it's going to be 7 minus 3 minus 2i. Sum like terms, 7 minus 3 is 4, minus 2i. 4 minus 2i. Here we go. Simplify this. So it's just 4 minus 6i plus 3i. Sum like terms, so it's just going to be 4 minus 3i. Okay, so the answer is A. Pretty straightforward on this one. Again, the biggest thing is make sure if there's a negative sign in front of a group of parentheses that you distribute it. All right. For two imaginary numbers, bi and ci, if you multiply them, it's going to become negative bc. Remember, I squared is negative 1. Don't forget that. All right, so find 5i times negative 4i. So it's going to be negative 20i squared. I squared is negative 1, so the answer is positive 20. Okay, so find, and let's do this together, 2 plus 3i times negative 3 plus 5i. So we're going to use distributive property. So 2 times negative 3 is negative 6. 2 times 5i is 10i. 3i minus 3 is negative 9i. And 3i times 5i is going to be 15i squared. Sum like terms, I got negative 6 plus I minus 15. Because remember, what's I squared become? Negative 1. So I can simplify this to be negative 21 plus I. Okay, next example. Simplify. 12 times 7 is 84. I squared. I squared is negative 1, so it's just going to be negative 84. Next one, simplify. So I got 6 minus 5i times 4 minus 3i. So distributive property, 6 times 4 is 24. 6 times negative 3i is negative 18i. Negative 5i times 4 is negative 20i. Negative 5i times negative 3i is going to be 15, positive 15i squared. So I'm going to rewrite it. 24, we can sum like terms, minus 38i, okay, minus 15. Because remember, what's I squared? Negative 1. So this is just going to be 9 minus 38i. So the answer would be A. 6C, simplify, okay. 16, 4 times 4 is 16. 4 times 3i is 12i. Negative 9i times 4i is negative 36i. And negative 9i times 3i is going to be negative 27i squared. So it's going to be 16 minus 24i plus 27. Remember, the I squared becomes negative. So 16 plus 27 is 43. So it's going to be 43 minus 24i. Okay, moving on. Some quadratic equations have solutions that are complex numbers. So for example, finding complex solutions. Solve 4x squared plus 100 equals 0. So we set it up, 4x squared plus 100 equals 0. We're going to isolate the variable, so I'm going to get 4x squared equals negative 100. I'm going to get x squared, divide each side by 4, equals negative 25. So x is going to equal plus or minus the square root of negative 25. So x is going to equal plus or minus I times the square root of 25, which is going to be x equals plus or minus 5i. Okay. Moving on to the next section.